let's look at a couple of applications of charges in fields and how they might move, kind of things. Okay, so first off, this we're going to just do a simple problem here with what's called a dipole. Dipole is, di means two poles, so it's just two charges stuck together, right? Two charges. Okay, and so this would be our dipole here. They're stuck together somehow. We'll just do an example where the charges are the same size, but you could have, I suppose, charges of different sizes. Lots of times maybe the application would be when you have small atoms and things where you're looking at the charges that are separated somewhat and trying to do calculations of what might happen to these atoms when they're put into an electric field. All right, so we've got some things we're supposed to find: d, p, and t, torque, tau, and show the motion. So here's our little dipole. Our definition of our d vector is a vector that goes from the negative to the positive. So d goes from minus to plus. All right, and so we're going to define a p vector. That was a d vector. The p vector, the p vector is just q times the d vector. All right, so p, the dipole moment, we call it, is what we call dipole moment. Dipole moment. And then we have the equation, let's just go to a pencil, the torque. So remember, the torque is a twisting force, right? How it's going to spin. Each one of these is going to have a force on it because of the field. Two charges are each going to have a force because of the field, and so we're going to get a torque that makes the dipole, the two charges stuck together, spin. So torque is just P cross E. Let me just double check I got those in the right way. Yes. And so remember, from the definition of a cross product, we can write it as scalar P, scalar E, sine theta, the angle in between, right? And so when the two vectors that make up a cross product are perpendicular to each other, then sine theta is 90, so we get our maximum or minimum torque, right? The maximum magnitude, we should say. Right? When the angle is 0, when they're lined up with each other, we get no torque, right? Because sine theta is 0, sine of 0 is 0. All right, so and theta is angle from P to E, the angle between the two vectors. So okay, so it says to show the motion. So what's going to happen here? So what happens when we have charges in the field? Let's just kind of draw some little forces on here. So this is a negative charge. I said on this side is a negative charge. And so what happens to negative charges in an electric field? They feel a force, right? And the force is parallel to the field. But is it going to be with the field or against the field? Well, negative charges feel a force against the field. So this one will have a little force minus going that way, whereas a positive feels a force with the field, so force plus is going to go that way. And so the motion, the torque, the motion will be like this, right? This positive goes that way, negative goes that way, so it's going to turn like that. It's going to turn until P lines up with E. So it's going to end when P and the external field are together. So remember, these lines here that I've drawn here are not the field from these charges, right? They're going to generate their own field in different places. It's going to go from minus to plus inside here. So the P kind of lines up with the field of the dipole itself, but this is an external field caused by something else setting up a uniform field out there. And so what happens is they line up, and the field, basically the two fields line up with each other. The field of the dipole inside here anyway, it'll have different kind of field around it, but in the middle will line up with the field there. Okay, so we've got D, well, Let's just say D is 10 to the negative, I have no idea, 10 to the negative 9 meters. And what else do we need? Let's say Q is 5 microcoulombs. And let's say the external field is, I don't know, 100 newtons per coulomb. Totally made up numbers, have no idea if they're anywhere close to realistic. But let's figure, and let's get an angle here too. Let's say this angle, what does it look like? About 50 degrees. Okay? And so let's calculate, let's get the torque as a number then. So we need P, or we can just say P is QD. And so we could say then our torque magnitude wise is QD, whoops, don't forget the E external sine theta. All right, so Q, I just said 5 micro, 5 times 10 to the negative 6 coulombs. D was 10 to the negative 9 meters. E was 100 newtons per coulomb. Sine of theta. So is theta 50 degrees or is theta something else? 50 degrees is just given on the picture, but the sine theta for this equation is the angle between P and E. So we start on P. P is like this, and we go to E like that. So it's not 50 degrees, right? Let's kind of draw it out here. So P is this way, and E is this way, and so it's the angle here is theta. Right, so this one is 50 degrees, and so theta is 180 straight line minus that 50 degrees. Okay, so let's put in torque, or put in the numbers for torque. 5 E negative 6. Okay, looks like you can see that. 5 E negative 6 times 1 E negative 9 times 100 times sine of 180 minus 50. Okay, I chose small numbers, but it's a small thing, so I'll have a small torque. So the torque is 383 times 10 to the negative 15 watts. What are the units? Let's just double check here. So coulombs cancel, and we get Newton meters, which is the correct unit for torque. So that's good. Okay, so just we can get some twisting motion, rotational motion because of electric fields and such. And so equation to have on your equation sheet would be good there. All right, another kind of motion. This would be like electron gun, electroscope, things that cathode ray tubes, things shooting particles, charged particles, old-fashioned TV screens and so forth used to have stuff like this. All right, so let's say we have a charged particle, has some sort of charge Q. I'm not saying if it's positive or negative at the moment, but it's got some initial velocity, and it's going to go in between these two plates. So these are two conductors, conducting plates, and one has positive charges on it and the other has negative charges on it. And we'll say that the charge density, the area charge density is 20 microcoulombs per square meter. All right, so we have charge densities, linear, volume, surface, and so this is a surface charge density or an area charge density. So what's going to happen when a charge goes in here? It's going to feel the field. Let's see, what is the field going to look like inside here? Field always comes out of positives and goes to negatives. So this field, and especially straight in between, and I'm not drawing very uniform, but it should be uniform. All right, it should be going on the edges. It might bulge out a little bit, but we'll kind of ignore the bulging effects. And so we've got our E field inside here is going from positive to negative, so it's going down, right? And so if I say my particle is going to end up going downward in the field, right? So it's a charge, it's in a field, it's going to feel a force, right? And so if it's a positive charge, well, so I wanted to know, I say it's going down. So is it a positive charge or a negative charge? If it's a positive charge, what do? They feel a force in the direction of the field, right? And so that agrees with what I've drawn here. If we're a negative charge, it would feel force in the opposite direction of the field, so it would be pulled up. And so most of the time you would have electrons and it'd be negative charges, and they'd be pulled in the opposite direction of the field. But in this case, I said the way that I drew my picture says Q is greater than 0, right? So Q, like I said here, then will be plus 5 microcoulombs. Alrighty. And so we want to find the final velocity and we want to find the final y. So we want to find how far down off of the center grid. So if we call this our x-axis and this our y-axis, y final is just how far it's gone. Basically, y final will be below the y-axis. Okay, how far it's gone below the y-axis. All right, so how can we do this? We know that we're going to have a force, but then we want to find position and velocity. So it sounds like a mixture of electric stuff, Coulomb's law stuff, and electric field stuff, and kinematics. All right, so remember our kinematic equations from before. I guess we'll just write everything. So x equals x naught plus v x naught t plus 1/2 ax t squared. V equals vx equals vx naught t vx naught plus at ax t. All right, so we have these in the x and y direction. So we have y equals y naught plus vy naught t plus 1/2 ay t squared. Vy equals vy naught plus ay t. All right, and so these are for constant acceleration, which we're going to have a constant field, we'll have a constant force, we'll have constant acceleration, so we can use these equations to figure things out. We'll have some velocities and things will be 0, some accelerations will be 0. So we're going to ignore gravity. We're going to say that the electric field force is a lot bigger than gravity, and so the only acceleration we'll have is due to the electric field, things like that. So comes in with v naught. It's got a horizontal velocity, straight horizontal. All right, and so that means at the beginning, all these not conditions, right? We have only x, only velocity in the x direction, and both x and y are 0. X naught and y naught are 0, and vy naught is 0 because there's no velocity up and down, there's only velocity sideways. So x naught is 0, y naught is 0, vx naught is not 0, but vy naught is 0. All right, so all of these things are 0. Looking at acceleration, the field is going straight down, so it doesn't have any component of, it doesn't cause, so the field and the forces are all straight down, and so it doesn't have any sideways components, so ax is also 0. There's no force in the x direction, there's no acceleration in the x direction, it just has the initial velocity, initial kinetic energy going in, and well, that's a lot of things that are 0. And so Vx naught is V naught, right? Vx naught, all of the velocity at the beginning is just from the x. So it's going to get some velocity going down eventually because of the acceleration from the force going down, but at the beginning, all the velocity is just V naught. So so then we're going to have Ay, right? So Ay is what's happening because of the force of the electric field. So let's go ahead and get the force of the electric field. The force of the electric field is going to be Q times the electric field. That's kind of our defining equation for finding electric fields. We've got the directions, so let's just do this magnitude-wise because we're taking care of the directions with these equations. And so, what is the electric field? Good question. So, we can't just use point charge stuff because we don't just have one charge. We have a whole row of charges here and a whole row of charges here. So we have another equation. It's on your equation sheet for for the field between parallel plates. And so E is just sigma over epsilon naught. And so it's kind of strange, but to the charges, to the field here, it doesn't matter where you are. Up here, down here, the field doesn't get stronger or weaker any place in here. So it doesn't depend on y at all. It's just sigma over epsilon naught. Sigma is the density, so it depends on how many charges we have in between the plates. And epsilon naught is just a constant. Remember, K is 1 over 4 pi epsilon naught. Epsilon naught is just a constant. And so anyway, we can just plug this in. So we got Q sigma over epsilon naught. So Q is the charge of our little particle that's flying through here because it's going into this field. And so Q is 5 times 10 to the negative 6 coulombs. Sigma is 20 microcoulombs. Again, I'm just making up numbers. 10 to the negative 6 coulombs per square meter. And epsilon naught is 8.854 times 10 to the negative 12. Oh, what are its units? I got a peek. I have on the back side here. Coulomb squared, Newton per meter squared. Coulombs squared per Newton meter squared. Alrighty, so let's just take a peek at those units. So we got coulombs squared over meter squared. So that's on the top, and that's also coulomb squared per meter squared on the bottom. So on the bottom we have 1 over newtons. So that's going to come to the top as newtons. So then the force will be in newtons. So that is all good. Okay, so let's calculate this thing. So we got 5e negative 6 times 20e negative 6 divided by 8.854 e negative 12. That looks like it. 11 point. We'll just keep 3 sig figs for today. 11.3 newtons. All right. Well, I guess we're not done. Let's keep 4 until we get, because that wasn't the final answer. 11.29 newtons. We got a ways to go yet because we're trying to find velocity and y. Okay, so that is our force. What good does that give us when we're trying to get all this position stuff? Well, Newton says force equals mass times acceleration. The total force, the net force, total force equals mass times acceleration. And so in this case, I said we're ignoring gravity, we're ignoring outside forces. The only force is the electrical force. And so we can say that A equals F over m. Oh, yeah, I gave an m too. All right. So the acceleration is going to be this force, 11.29 newtons, divided by the mass. Ooh, maybe that's kind of a big number, but anyway, that's what I said. I put in there. So 10 to the negative 20 kilograms, a tiny little, like electron-sized particle, maybe, pretty small. And so we get 11.29 times 10 to the 20th. Ooh, that's going to be big. Meters per second squared. All right, so this is A. This is the acceleration because of the field. It's in the y direction, so in terms of these equations over here, this is AY. AY. Okay. So what do we want to do? We want to find VF, the final velocity. We've got V in the x direction, it just stays the same. Vx final is going to be Vx initial because the acceleration is gone. So it doesn't matter. So Vx, maybe it's called V final sub x equals V initial sub x equals V naught, right? Equals 20 meters per second. V final sub y is going to be, that one is 0, so it's going to be AY times T, but we don't know T. Similarly, Y final here, Y naught is 0, Vy naught is 0, is just going to be 1/2 AYT squared. So those are the things, well, we want the total velocity as a vector. So we got the x part here, y part we could find here, and then we want the final position, how far down past the bottom of the center, how far past the center down does it go, but we need time. So how can we get time from all this? Well, we can use this x equation to figure it out, right? And so hopefully your notes will be prettier than mine, but I'm trying not to have to turn the page here. So let's look at this equation again. So we've got x equals, and we'll call x final. Let's make a little box for doing this. So x final is x naught, which is 0, v x naught t, which is v naught. I guess I'll just write it in general, v naught sub x t, and then the acceleration of the x is 0. So that's all we've got. So we can get t from this. So t is x final over v naught x. X final is just started here, ends here. We said the length is 0.5 meters, so x final is 0.5 meters, and Vx naught is V naught is 20 meters per second. All right, so t, I'm going to have to flip the page. Come on, paper. So t is 0.5 meters over 20 meters per second, so it comes out to be seconds. So 0.5 divided by 20 is 25 milliseconds, or 0.025 seconds equals t. I don't know about that. And then, so let's just copy some stuff over. So v final sub x, we said was 20 meters per second because it didn't change in the x direction. And then v final sub y was ayt, but ay we got as 11.29 times 10 to the 20th, ooh, big number, times 0.025. So we're going to have a lot of acceleration. Anyway, probably crazy numbers, but 11.29 E20 times 0.025. 28 point, I'll just go with 28.2 times 10 to the 18th meters per second. Okay, anyway, we're going with it. And then y sub f, well, let's get velocity, the total velocity then. So v f as a vector then is 20 I hat plus 28.2 times 10 to the 18th j hat meters per second. All right, pretty weird number. And so the 20 is going to be insignificant compared to that. So if you wanted to get the rough velocity, it's going to just be all down and no sideways. All right, so numbers are not very realistic. Y sub f, this is probably going to be crazy also. So y sub f, looking at our notes, y sub f is 1/2 ay t squared. And our ay was crazy, so 1/2 11.29 times 10 to the 20th times t, which is 0.025 squared. So yf 0.5 times 11.29 E20 times 0.025 squared. Yeah, 353 times 10 to the 15th meters. Alrighty, so it's way gone out of, I don't know what kind of machine could ever look like this. This is ridiculous numbers, but process is okay. All right, so hopefully you see the process. What did we do? We figured out our electric field inside of here, figured out the force on the particle, right? And then we used that force, used Newton's second law to get acceleration. We used our kinematic stuff, looking at our initial conditions, how things were oriented, so forth. Lots of things were zero. plugged in to find what we wanted. We needed to find T, used X to get T, and then used Y information got Y information once we got T. All right, so let's stop there.